Hello everybody. How are you all doing on this wonderful day? I hope you're doing well. I hope you are being safe. I hope you are practicing social distancing. I hope you are washing your hands, keeping your hands clean, and all of those wonderful things. And I cannot leave out, I hope you're staying home. Very important, very important. Okay, today we're going to look at absolute convergence as it relates to conditional convergence and as it all relates to divergence as well. Okay, so that's what we want to talk about today. We want to talk about the absolute convergence of any given series. All right, so first let's go back just a little bit and look at some of the series, not all of them, just a few of them. Okay, let's recall, if you will, given a series AN, where AN, of course, is the sequence, but when we put a summation on it, it becomes a series, right? The series AN, there's the nth term test for divergence, which simply states that the series is divergent if the limit as n approaches infinity of the sequence does not equal 0. If it equals any other value, or even include infinity, then the series is divergent. If it equals 0, inconclusive. Okay? It could be convergent or divergent. We don't know. But if it equals 0, if it doesn't equal 0, it's divergent. P-series test. Okay? Well, if the sequence AN is 1 divided by n to the power of p, well, the series converges if p is greater than 1, strictly greater than 1. That's what we call a lax, L-A-X, a lax inequality. If it's strictly greater than 1, and the series diverge if p is less than or equal to 1. That's divergent. All right, that's the p-series. Then there is the famed ratio test. Okay, the ratio test says what you do, you look at within the series, you look at the sequence, right? You look at the sequence, and you find the limit as n approaches infinity of the absolute value of the ratio of the succeeding term divided by the preceding term. A to the n plus 1 subscript divided by a to the n. All right? This, ladies and gentlemen, is in essence absolute convergence because it has the absolute value notation and the absolute value bars here. See that? That implies absolute value, the vertical lines. So this absolute value is, in fact, what we're learning today, what we're talking about, which is what? Absolute convergence. See, there's the bars right there. And so when we apply the root test, we are actually looking at absolute convergence if the series converges. Absolutely. We don't know. Have to see. But, so the ratio test is the limit as n approaches infinity of the absolute value of the succeeding divided by the preceding terms. If the limit is less than 1, if the limit is less than 1, it's convergent. If the limit is greater than 1, it's divergent. If the limit equals 1, then the test is inconclusive. We don't know whether the series converge or diverge. You might want to try another test. Try another test if it's equal to 1. Test doesn't tell us anything. All right, then we have the alternating series test. 3 conditions on that. There are 3. Condition number 1, AN, the sequence, must be positive. That's our first condition. AN has to be greater than 0. Condition number 2, AN has to be decreasing. Okay? And the way we can tell whether or not it's decreasing is you take the sequence AN, you can find its derivative, right? And once you find its derivative, then all the values of n plugged into the derivative should render or yield us a negative result. That implies that it is decreasing, because we know when the first derivative is negative, then at some point, you know, the graph is decreasing. It's going down. All right? So that's second condition. And third condition, the limit as n gets increasingly large of the sequence, that limit has to equal 0. If those three conditions are true, then by the alternating series, we can say that it is convergent. The series is convergent. All right, then there's the direct comparison test, which says if I give you a sequence, right, and that sequence, which is a part of the series of AN, if I give you that series AN, you have to determine another series. You have to do that. You determine the series Bn. You see that? Here's the series Bn. And for that series Bn, if we have AN less than Bn, the sequence, then if the series Bn is convergent, then the series AN is convergent. If the series AN is divergent, then the series Bn is divergent. So I guess a good way to look at it is like this. For our condition where Bn is bigger or greater than AN, right? If the larger one converges, the smaller one is pulled along and converges. If the smaller one is divergent, then it pulls the bigger one down. It also diverges. So look at it in terms of the polar opposites. Big, small. See? Big going up, small going down. If the larger one converges, then the smaller one converges. If the smaller one diverges, then the larger one diverges. And that's it. We don't know what happens. It's inconclusive if the larger one diverges. We don't know what happens. Inconclusive. Or if the smaller one converges. We don't know. So if you're larger, you converge, you're pulling up the smaller one. If you're smaller and you diverge, you're pulling down the larger. That's the direct comparison test for series. Okay? And then lastly, we have the limit comparison test. This is a very nice test. The limit comparison test. So what it tells us is that if we have, again, we're looking at two series here. And it doesn't matter which one's largest, which one's smallest, which one's greatest, which one's less. Doesn't matter. What does matter is if you take the limit, as in it's very large, of the ratio of either what? AN divided by BN or BN divided by AN. It doesn't matter. It does not matter. Okay? If the limit L is greater than 0 on both, or either one, either this ratio or this ratio, if the limit is greater than 0, then what that means is if AN converges, then BN converges. If AN diverges, then BN diverges. If BN converges, then AN converges. If BN diverges, then AN diverges. That's all it means for the limit comparison test. What one is doing, so is the other. So whenever you use the limit comparison test, it's helpful that you at least know whether AN is convergent or divergent, or if BN is convergent or divergent. You have to know what at least one of them are doing. Because whatever one is doing, so is the other. So you have to be able to understand either AN or BN. If not both, but at least one of them. Okay? Because what one does, see that? So does the other. What one does, so does the other. So if the series AN converges, then the series BN converges. If the series AN diverges, then the series BN diverges. If the series BN converges, then the series AN converges. If the series BN diverges, then the series AN diverges. Okay? So one does whatever the other one will do. That's what the limit comparison test tells us. Okay, so today, here's the lesson. Bam! Right there. So the series AN is absolutely convergent if the absolute value of AN is convergent. So here's the point. If the absolute value of the series is convergent, then the series without the absolute value is convergent. If the series with the absolute value is convergent, then the series without the absolute value is convergent. Okay? So absolute convergence is exactly what it means. The series is absolutely, no ifs, ands, buts about it, convergent. Okay? Conditional convergence. AN, the series AN is conditionally convergent if the series AN converges and series absolute value AN diverges. So it's always good to start with absolute convergence first, because you see what happens is this. If you look at the absolute convergence and that series diverges, it does not mean that the series without the absolute value will be divergent. It can be conditionally convergent. So it's best to check in that order. Check for absolute convergence first, and if that's divergent, then check for conditional convergence second. Okay? But what comes before those two things? What comes before absolute convergence? And what comes before conditional convergence? Well, you should always start off with the what? Nth term test for divergence first. Try that first. The nth term test for divergence. And if then that doesn't work, or if that doesn't give you any information whether or not the series is divergent, then go into what? Absolute convergence. And then check out conditional convergence. So that's what we want to do right now. We're going to put some examples here, right? And we want to determine if the series that's going to be here, if they are absolute convergent, conditionally convergent, or just outright divergent. So for all the series we put here, tell me whether or not the series are absolutely convergent, conditionally convergent, or just outright divergent. Okay? All right, here we go. Let's look at a few examples. Example 1. All right, example 1. Here's our series. N equals 1 to infinity of -1 to the n of n cubed divided by 3 to the power of n. All right, so let's determine whether or not this series is, if it converges absolutely, if it converges conditionally, or if it just outright diverges. Okay? If you ever want to pause the video and try it on your own first, go ahead and do it. Try it. Then come on back and we'll work through it together. Okay? All right, come on, let's go. Well, the first thing I'm going to do, I'm going to see whether or not the series is divergent. I'm going to use what we call the nth term test for divergence first. So within that series, I'm going to take the sequence. The sequence is a to the n. A to the n, that's the sequence. And see whether or not that limit equals 0. If it equals 0, it's not helping me. If it doesn't equal 0, I'm finished with the problem, because the problem is divergent. The series is divergent. All right, so in this case, here's what we know. We know a subscript n is n cubed over 3 to the n. Okay? The -1 to the n is not a part of the sequence an. That just lets us know we have an alternating series that goes back and forth. In this case, it goes negative, positive, negative, positive, negative, positive, negative, positive, negative, positive, negative, positive. So that's all this right here tells us, is that we have an alternating series. Okay? Which in fact, we may have to use that. We may have to use the alternating series right here. Okay? So first we're going to check for absolute convergence. Once we check for absolute convergence, if it's not convergent, if it's divergent, then we're going to go back and check it and see if it's conditionally convergent by using the alternating series test, because it alternates. You see that? That's important. All right, come on. So let's look at the limit. All right, let's consider the limit as n goes to infinity of n cubed over 3 to the n. What does that equal? Okay. Now, at this stage, you should not be confused or not be doing a lot of work, because you have to remember what we taught you in terms, and what we said in terms of the comparative growth factor. That's important. The comparative growth factor. What did we say? We said that logs grow at a slower rate than the algebraic, and the algebraic grow at a slower rate than the exponentials, and the exponentials, they grow at a slower rate than the factorials, and the factorials grow at a slower rate than the variable exponentials. Okay? So what do we have in this case? In this case, we have an algebraic, because n cubed is algebraic. Divided by 3 over n, well, that's exponential. And so we have the slower over the faster. And when we have a slower over faster, as n gets increasingly large, then we know that this right here goes to infinity. No, I'm sorry, it goes to 0, pardon me. I'm saying one thing, writing something different. It goes to 0. Because a smaller number, as the numerator becomes increasingly small, the denominator becomes increasingly large. So it's like having a small number divided by a very large number, and that gets closer and closer to 0. Okay? If it were the other way around, if you had like anything large number divided by a small number, then that goes to infinity. But this approaches 0. And since this approaches 0, what does that tell us? Oh, well, doesn't tell us a thing, because that equals 0. Man, we know this sequence, along with this series, would be divergent if what? It's divergent if the limit didn't equal 0. If it does not equal 0, then it's divergent. But since it equals 0, it tells us nothing. Don't know if it's convergent or divergent. So that means the interim test for divergence really didn't help us. We have more work to do. We have more work to do. Okay, so first, let's go after absolute convergence. So first, I'm gonna find, let's look for absolute convergence. How am I going to do that? Well, in this situation, I'm going to use the ratio test. I'm going to use the ratio test. Okay? I'm going to look at the limit as n goes to infinity of, here it is right here in purple, absolute value. The next term up, n plus 1 cubed divided by 3 to the n plus 1. See that? Now that should be divided by an, but instead of dividing it by an, I'm going to multiply by the reciprocal of an. Instead of dividing by an, no, multiply by the reciprocal. So I'm going to multiply this times, instead of doing n cubed over 3n, I'm going to multiply it by the reciprocal, which is 3n over n cubed. Okay, everybody good? You good with that? You good? All right, now I'm going to algebraically separate this out somewhat. Watch how I write this now. So I'm going to keep n cubed, n plus 1 quantity cubed. So I have n plus 1, that quantity is still cubed. All right, times 3 to the power n divided by, okay, here we go. Now you see this n, this 3 to the n plus 1, which really should have parentheses around like that. You see this 3 to the n plus 1? I'm going to split this up using the laws and rules of exponents. So this is 3, so this is 3 to the n times 3. 3 to the n times 3 is 3 to the n plus 1. So now I'm going to write this over there. But I want to line up my 3 to the n's. I'm going to put a 3 to the n right here, and I'm going to put times 3 right there. And then this n cubed, I'm going to write it under this term right here, n cubed, like that. We're going to write it like that. Okay, here we go. So the limit, as n gets very large, all right, let's see what we can cancel out. The 3n goes there, the 3n goes here. All right, so I'm going to have n plus 3 quantity cubed over 3n cubed, which equals the limit as n gets very large. All right. I think in this case, I'm going to factor out a 1/3. So let me write it like this, 1/3, the limit, as n goes to infinity of n plus 3 cubed over n cubed. All right, and that's going to equal, I can rewrite it again, as 1/3, the limit, as n goes to infinity of, here it is, n plus 3 over n, and now this quantity is cubed. Again, laws of exponents, exponential rules, exponential laws. All right. Let's see, so what do we have here? We have 1/3, the limit, as n goes to infinity of, I'm going to rewrite this again. N divided by n is 1. 1 plus 3 over n cubed, which equals 1/3. Oh, I'm sorry. Yeah, that's right. Which equals 1/3. All right. Now, as n goes to infinity, where does this go? Well, as n goes to infinity, 3 divided by infinity, this goes to 0. So I'm going to have 1 plus 0, which is 1, times 1 cubed is 1. So it's 1/3 times 1, which equals 1/3. Okay. Now, go back to the ratio test. The ratio test says, here it is right here, ratio test. It says if the limit is less than 1, we have convergence. Our limit here is 1/3. It converges. And it converges absolutely. So 1/3 is less than 1. 3 dots. Therefore, that's what 3 dots mean. Therefore, the series converges absolutely because of the ratio test. There you go. The series converges absolutely because of the ratio test. All right? We tried the interim test for divergence. It failed. And then we tried and we checked for absolute convergence. And we used the ratio test, which is already an absolute convergence test because it already has absolute value. So it's an absolute convergence test. Okay? The ratio test and the root test are absolute convergence tests. And when we did the ratio test, well, we got a limit of 1/3, which is less than 1, so it absolutely converges, so you don't have to do anything else to this problem. All right? All right, that's our first example. Let's do another one. That's example 1. So it absolutely converges. What I just erased regarding the logs, the algebraic, the exponential, or factorial, we're going to come back to that over and over and over again. That comparative growth dynamic. That's important. All right. Let's go. Example 2. Let's see what we have here now. 1 second ago. Example 2. N equals 1 all the way up to infinity of -1 to the n times n over n plus 1 to the power of n. And we want to know whether or not the series absolutely converges, whether it conditionally converges, or whether it just outright diverges. I don't know. Let's see. So, again, first, check to see if the series diverge. Because if it diverges, there's no work to do. Let's see if it diverges first. That's first. So, always start with the what? Interim test for divergence. All right? By taking an and finding the limit as n gets increasingly large. So our an is n divided by n plus 1, all this to the power of n. Let's go after the limit. So we want the limit as n goes to infinity of n divided by n plus 1 to the power of n. Okay? Now, if we look at this limit, we know that as n gets increasingly large, in our parentheses here, that's a power 1, that's a power 1. So when we look at, if you go back and recall our study of infinite limits, we know that if the power of the variable in the numerator and the highest power of the variable in the denominator, if those powers are the same, then the limit will approach the coefficient, or the quotient of the coefficient of those variables. So the quotient of our coefficient here is 1 divided by 1. And 1, and I'm talking about the coefficient here, which is 1, and that's 1. So 1 divided by 1 is 1, so this limit is going to equal 1. And then put infinity in for n right here, it's going to be 1 to the infinity. It's 1 to the infinity. Now, we know when we studied L'Hopital's rule that 1 to the infinity is an indeterminate form And it's one of those 7 indeterminate forms that we can't actually use L'Hopital's rule as a result of this 1 to infinity. We can't use it, so we're going to have to kind of manipulate it and put it in another form, where it's either going to render us a 0 divided by 0 or an infinity divided by infinity, because those are indeterminate forms in which we can apply L'Hopital's rule. Okay, those forms there, those 2 forms. This form, we can't apply L'Hopital's rule to that indeterminate form. So how do we rearrange it? What should we do? Well, notice this. We have 1 to infinity. We have 1 to a power, so we have to get the power from up there and bring it out front. You know, we have to move the power down. And the only way to move the power down is by taking a log, using natural logarithms. Okay? So let's use some logs now. All right? So first we want to just set it equal to y. Let's see. Let's let y equal the limit as n approaches infinity of n over n plus 1 to the power of n. Okay? So Mr. Wright, you say, well, where did y come from? Why are you saying let y equal? Why are you using y? That goes back to when we learned about logarithmic differentiation. Remember that? You recall logarithmic differentiation? When you were asked, for example, to find the derivative. Let's see, what's the derivative of x to the power of x? See that? And the only way you can differentiate such a problem is you have to use a logarithmic differentiation, right? You have to let y equal x to the power of x, and then take the natural log of both sides. And now you can use the power of logarithms. You can use the power rule of logarithms and bring the power to the front. So that becomes x natural log of x. So that's why I'm using y right here. That's why I'm using y, because in order to use L'Hopital's rule, it involves some differentiation. Okay, it involves differentiation that involves a power here. So we have to kind of go back and recall this somewhat. All right, let's keep on going. All right, so we have to take the natural log of the left side, which equals now the natural log of the limit as n gets increasingly large of n divided by n plus 1 to the power of n. Okay, good. So now we're pretty much structured and we're ready now. We're ready to take that power of n and move it to its proper location as a result of this natural log. All right? And so now this is going to equal, now natural log y, I'm going to do these quotation marks just to bring it down, right? And now I'm going to go ahead and rewrite this as the limit as n approach infinity of the natural log of n over n plus 1 to the power of n. And the reason I can do that, I can rearrange it like that, is because my argument, n divided by n plus 1 as n gets increasingly large, is a continuous function. And since the function is continuous, I can now look at the limit of the natural log. Instead of looking at the log of the limit, I can look at the limit of the log now. Because our argument is continuous, I have a continuous function here, so now I'm looking at the limit as n gets increasingly large of the natural log of that argument, which is n divided by n plus 1 quantity to the power of n. All right, so now we have it. Let's keep going. Let's erase this. So we have natural log of y. And it does equal, let's use the power rule now. It equals the limit as n gets increasingly large of n, the natural log of n divided by n plus 1. All right. Well, what is that going to give us now? Now go ahead and plug in infinity for n. If I put infinity right here, and if I put infinity right here, well, what this is going to do, if you look at n divided by n plus 1 as this goes to infinity, it's the same thing we did right here. It's the same result, guys. The result is no different. It's just that in this case, if infinity goes in for n, that's going to give me infinity times, okay, now put infinity for n over here. Well, that's going to be the natural log of this goes to 1. 1. And what is the natural log of 1? 0. The natural log of 1 is 0. So I have now infinity times 0. And that's still indeterminate. So I had an indeterminate form right here. We have an indeterminate form here again. So that means we have to keep on working and manipulating our limit until we find a form that is indeterminate, that's L'Hopital ready or L'Hopital evaluative. This is not L'Hopital evaluative. We have to keep going until we get to L'Hopital evaluative. All right, here's the good news. Whenever you have infinity times 0, that means you're one step away. You're one step away. Here it is. Here's the big move right here, ladies and gentlemen. You see this n right here? That n? You have to look at that n in terms of 1 divided by 1 divided by n. That's how you have to rewrite it. N has to be rewritten as 1 divided by 1 over n, this quotient here. Because this does equal what? N. So it's a matter of how you rewrite the n. Let's do it. So I have the natural log of y, which equals the limit as n gets increasingly large of the natural log of n divided by n plus 1 all divided by 1 over n. All right, now let's go ahead and look at the limit as n goes to infinity. Now what's our result? Well, again, this here, this goes to 1, and the natural log of 1 is 0. As n gets large, 1 over a very large number also goes to 0. Congratulations. We now have 0 divided by 0, which means we can apply L'Hopital's rule, which states that if the limit as x goes to infinity of f of x divided by g of x, if it is either 0 divided by 0 or the infinity divided by the infinity, then we can apply L'Hopital's rule, and all of that will equal the limit as the differentiation of f of x divided by the differentiation of g of x. Boom, and there you go. That's how we determine the limit. So let's go ahead and try that now. So natural log of y is going to equal. Let's go ahead now and apply L'Hopital's rule. Okay? Well, we have the natural log of n divided by n plus 1. We know that the derivative of the natural log of u, it equals u prime divided by u. That's the rule for natural log. It's u prime divided by u. Okay? So we have to use the differential rule here for natural log, because that's what we have. We have the natural log of the argument n divided by n plus 1. So that's what we have to use. The derivative rule for natural logarithms. All right, so here we go. So it's going to equal the limit as n gets increasingly large. All right, let's go ahead and differentiate this. All right, so in this case we have to use our quotient rule, because we have n divided by n plus 1. So it's going to be low, which is n plus 1, times the high, which is just 1, minus the high, which is n, times the low, all divided by square below. This quantity is squared, all divided by n plus 1. All right, so this gives us our derivative of the natural log of the quantity n divided by n plus 1. It's the quotient rule up top divided by what's down below. All right? In fact, this should be the whole thing, which is n over n plus 1. Yeah. So it's the derivative of all of it, which is n plus 1 minus n divided by n plus 1 quantity squared, divided by the whole thing, n divided by n plus 1. So that's what we have. Long line here. This divided by that. All right? But we're not done. That's just the numerator. Now we have to do the denominator. So it's all of that divided by, okay, what's the derivative of the denominator? What's the derivative of 1 divided by n? That's going to give me negative 1 over n squared. And I want the limit as this approaches n going all the way to infinity. There we go. So first, let's just deal with the numerator first. Let's just deal with the numerator. Okay? I mean, this is what we call a complex fraction. And it's complex because we have like a fraction within a fraction. You're dividing fractions of fractions, so it's called the complex fraction, right? So first, let's just deal with our numerator. Okay? So exactly what does this equal? What is this going to give us? So it's going to give us, well, I know that n plus 1 minus n is just n. And it's going to be n divided by n plus 1 squared. N plus 1, and that quantity is squared. All right? So that's going to be, well, no, hold on. The n's cancel out. That should be just the 1. The n's cancel out in the numerator. In the numerator, I have a positive n, a negative n, they cancel out. So it's 1 over the quantity n plus 1 quantity squared. All right, that takes care of this numerator. So now multiply it by the reciprocal here. That's going to be times n plus 1 over n. And all of that is still divided by negative 1 over n squared. Okay, let's keep going. Now, when we do this, please notice that the n plus 1 cancels one of the n plus 1's here. And you're only going to have 1 left. So we're going to have 1. So we're going to have the limit as n goes to infinity of 1 over n times n plus 1. And this is all divided by negative 1 over n squared. Let's multiply by the reciprocal once again, by negative 1 over n squared, by its reciprocal. So, and this is going to equal the limit as n goes to infinity of 1 over n times n plus 1, all right, times the reciprocal here. which is going to be n squared, negative, over 1, obviously, which equals, all right, let me see. Let's go and erase some of this stuff here. Let's erase this down here. Need a little bit more room. Let's erase it. So what is that going to give me? I'm going to lose an n. N going to cancel there. N's going to cancel there. So I'm going to have the limit as n goes to infinity of negative n. Negative n divided by, okay, what do I have? N plus 1? N plus 1. Negative n divided by n plus 1. Okay. There we go. Yep. I lose an n here. I'm left with one n. That n cancels out. So I have negative n divided by n plus 1. And that's what I have right there. And we know the limit as n gets increasingly large of negative n over n plus 1 is sort of like what we had a long time ago right here. Except for since this one was positive, it went to 1. See, this went to 1. But now since it's negative, it goes to what? Negative 1. Okay, very good. And so there you go. It's negative 1. And if you think negative 1 is your answer, you are incorrect. That's not the answer. And here's why it's not the answer. You have to go back and pick up right here. And right here. Don't forget this piece right here. This is so important. It's critical. Stuff's falling down. Do not forget this. You must bring that right on down to right here. So what we have now is that the natural log of y equals negative 1. We need to determine what y is. Okay? So that's the natural log of y equals negative 1. Alright, let's solve that. Well, if the natural log of y is negative 1, well, what's the base of natural log? The base of natural log is e. There's an e there. So to solve this for y, you have to do what I call wheels on the bus. You know, wheels on the bus go round and round, round and round, round. Okay, you get it. So go around. So when I say go around, here's what I mean. Start at the base, e, and make a circle. So go from e to 1, and then from 1 to y. Go around. So this means that e to the negative 1 power, e to the negative 1 equals y. So now, ladies and gentlemen, you know exactly what y is. Y is this. That's what y is. Y is e to the negative 1. Likewise, you know what y is right here. Now go back and grab it right here. Y is the limit as n goes to infinity of n divided by n plus 1 to the power of n, which equals what y is up here. E to the negative 1, which equals 1 over e. Okay? That equals 1 over e. And And what do you know about 1 over e? 1 over e is less than 1. It's less than 1. But since it's less than 1, that's not telling us anything. But here's what it does tell us. We know this though. It's less than 1, but also 1 over e does not equal 0. 1 over e is less than 1, but is greater than 0, but it doesn't equal 0 because of this right here. If it equals 0, we can't determine whether it's divergent or not. But since it doesn't equal 0, we then know that this series is divergent. Therefore, 3 dots. Therefore, 3 dots. The series is divergent because of the nth term test for divergence. Because of the nth term test for divergence. Therefore, the series is divergent. Why? Because our limit does not equal 0. Had it equal 0, can't tell you nothing. But since it's something other than 0, it's divergent. Okay. And so there you go. So once you find out it's divergent, there's no need in checking for no kind of convergence. It's not going to conditionally converge, it's not going to absolutely converge, it's strictly divergent. So with this problem, you had to kind of understand and go back and know what L'Hopital's rule is. Okay, you have to recall L'Hopital's rule and all those indeterminate forms. Okay, next problem. Let's see what's on tap next. Let's do another one. Well, aren't these a lot of fun? Aren't they fun? Some of y'all are like, no, this ain't no fun. It's like, no, man. This ain't. But then there are those that are like, yes, I'm really enjoying this. Good for you. Good, 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 good. Good. But some of these problems, you never know what you're going to get. Most of the time, I don't know what we're going to get. We just have to see how it turns out, you know? All right, example 3. Okay. Let's look at the series as n goes from 1 to infinity of -1 to the power of n of, all right, the square root of n divided by n plus 1. Let's take a look at that. Okay. Step 1. Take a look at the nth term test for divergence. All right, so our series is, here's the series. The series is an, which is the square root of n over n plus 1. All right. Let's look at our limit. The limit as n goes to infinity of the square root of n over n plus 1, which equals the limit as n goes into infinity of n to the 1/2 divided by n plus 1. And we know that does for sure equal 0 because the power in the numerator of the variable is smaller than the power of our variable in the denominator, which is a 1 right here. So we know that that equals 0. Okay? And since the limit of our sequence equals 0, that renders the interim test for divergence as being inconclusive. We can draw no conclusions. We don't know whether or not the series is going to converge or diverge. We don't know. So that means we have to go forward because we don't know what it's going to do. Okay? All right. Well, let's go forward then. So, how about we look at absolute convergence? Start with that. Let's see if it absolutely converges. So that means I'm looking for the sequence, or the series. Start with the series first. The series of the absolute value of the square root of n over n plus 1. Now notice that I do not have the negative 1 to the power of n included. I don't need that because that goes to 1. I know that this part right here is just 1. So I don't need that. Okay? I'm looking at this right here, the absolute value of it. Okay? And so this is going to equal absolute value of n go to 1 to infinity. And let's see what's going to happen here. The square root of n over n plus 1. So the question now becomes, what test will you use? What test will you use? Will you use the ratio test on this one? Will you use the direct comparison test on this one? Will you use a limit comparison test? Which test will you use? Okay? So let's see. Let's try a ratio test. Let's see if that works. I'm going to try the ratio test because I know the ratio test deals with absolute convergence. Let me try the ratio test and see what we're going to get. If I try the ratio test on this, then I'm going to have the limit as n goes to infinity of this term plus 1, the square root of n plus 1 divided by n plus 1 times. Alright, now take this and take the reciprocal of it. N plus 1 over the square root of n, which equals the limit as n goes to infinity. Alright, okay. The square root of n plus 1, I'm going to leave that there. N plus 1. And then the square root of n, I'm going to put it underneath it. Square root of n times n plus 1, that stays where it is. Right? And then this is nothing more than n plus 2, because 1 plus 1 is 2. That's going to be n plus 2 equals. Alright? And so this is now going to give me the limit as n goes into infinity of the square root. I'm going to combine these two. I'm going to combine these two here and make it 1. Just write it as one radical. Combine it. So that's going to be the limit as n goes to infinity of 1 plus 1 over n times n plus 1 over n plus 2, which is going to equal, here we go, as n gets very large, where does 1 over n go? As n goes to infinity, 1 over n goes to what? 0. So that's going to give me the square root of 1, which is just 1. That's going to give me 1 times, all right? And now if I do it right here and plug it in, well, what is that going to give me? Well, that's going to give me, coefficient is 1, coefficient is 1. 1 divided by 1 is just 1. That also gives me 1. So that equals 1. So if I use the ratio test, the limit equals 1. What do we know about the ratio test and the limit equaling 1? What do we know? Ratio test. If the limit equals 1, oh great. It's inconclusive. Inconclusive. So the ratio test didn't tell me nothing. It didn't tell me whether I'm convergent or divergent. Okay, that means the test fails, ladies and gentlemen. We have to try another test because this test fails. Okay. How about we try the comparison test? Let's try a comparison test on that. Let's see what a comparison test is going to do. And of course, this is the direct comparison test. So what do you want to compare it to? Well, I suggest that we compare it to the root of n divided by n. So whenever you have these rational functions, you might want to just use the direct comparison test. It's not a bad test to use. It's okay. All right, so let's compare it to it. So if we do that, then we know that our a subscript n is the root of n divided by n plus 1. And we know that b subscript n is just going to be the root of n over n. Okay? So these are our sequences here. Okay? So here we go. Let's see what's going on here. So notice that they're both positive, right? They're both positive. And here's what the direct comparison test says. They both have to be positive. Because see here, 0 less than a and a is less than b. So they're both positive. But now let's see if a is truly less than b. Let's see if a is less than b. Let's see if this is true. If the square root of n over n plus 1 is less than the square root of n over n. Notice, the numerators are the same. So there's equity in our numerators. They're both radical n. That's the first thing you have to notice. 2. Now go down to the denominator. N plus 1 is bigger than n, right? Which means if our denominator is larger, then the whole fraction is smaller. Larger denominator, smaller the fraction. Numerators are the same. They're equal. But when that's the case, if the denominator is larger than the other denominator, then that renders that whole fraction smaller. So yes, an is smaller than bn. All right? So now, let's rewrite this. Here we go. We can write this as the square root of n over n plus 1 is less than, let's rewrite this. This is what? This is n to the 1/2 over n. N to the 1/2 divided by n. We can rewrite it again. That's going to give me the square root of n over n plus 1, which is less than 1 over n to the 1/2. All right. Well, what do you know about 1 over n to the 1/2? What do you know about that? Convergent or divergent? Does it converge or does it diverge? Well, this right here, look at the p-series. Go back to the p-series. Here's the p-series right here. The p-series says 1 over n to the power of p. If p is greater than 1, we have convergence. If p is less than or equal to 1, we have divergence. Okay? So this does what? 1 over n to the power of 1/2, it is what? Correct, divergent. So this is divergent. So the series b to the n diverges. The only problem is this. If b to the n diverges by the direct comparison test, that's also inconclusive. Tells us nothing. Because look, for the direct comparison test, it says if b to the n, if the larger one converges, then the smaller one converges. And if the smaller one diverges, then the larger one diverges. But it tells us nothing if the larger diverges. This diverged. The larger sequence diverged, which means the test does what? Fails. Inconclusive. So the ratio test is inconclusive. The direct comparison test is inconclusive. All these tests are going to be inconclusive. Oh my goodness. Okay, it's time to wrap this up. Let's try one more test and we're done. I'm finished with this absolute convergence. We're going to try one more test. See if we can get a test that's going to tell us something. Let's look at the limit comparison test. Let's try that one. The limit comparison test. All right, same components, same elements. My goodness, this is incredible. Let's look at the limit comparison test. The limit comparison test. All right, so we have our an. An is the square root of n over n plus 1. All right, we have our bn. Bn is the square root of n over n. The limit comparison test now says if both of these sequence here are positive, and they are for every value of n from n equal to 1 to infinity, they're positive, right? Then we can look at the limit as n gets large of the ratio of either one, bn over an or an over bn. It doesn't matter. Just choose one of them, okay? Just choose one. So I want to look at the limit as n goes to infinity. Okay, which one you want? You want an over bn or bn over an? It doesn't matter. All right, let's go an, the square root of n, over n plus 1, divided by bn, the square root of n over n, which equals the limit as n goes to infinity of the square root of n over n plus 1 times the reciprocal, n, over the square root of n. All right, cancels out. So now we have the limit as n goes to infinity of n divided by n plus 1. All right, and as n goes to infinity, where does n divided by n plus 1, what does that equal? Where does that go? This goes to 1, because the power here is 1. The power is 1 with a coefficient of 1. The power here is 1 with a coefficient of 1. So that just equals 1. Uh-oh! Let's check it out. Let's see. I think we might have something here. I think we have something. The limit comparison test says, right, if either ratio, if the limit is greater than 0, and the limit is greater than 0, our limit was greater than 0, it was 1. That means whatever Bn is doing, then that's what An is doing. Or whatever An is doing, then that's what Bn is going to do. If one converges, then the other converges. If one diverges, then the other diverges. So you need to understand or know something about either An or B subscript n. Well, what do we know right here? We know that An we didn't know too much about An, but Bn right here, we know that Bn does what? Diverges. Which means if Bn diverges, then An diverges. Then by the limit comparison test, this absolute value of our sequence diverges. So we did all that to talk about this absolute convergence, and only to determine that therefore the series, the absolute value of An is what? Divergent. Which means it does not absolutely converge. No, 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 no. It does not absolutely converge. The absolute convergence of this is not the case. It is divergent. So since we know it does not absolutely converge, now let's check to see if it conditionally converges. Let's check the conditional now. Okay? So we know it doesn't absolutely converge because of the limit comparison test. All right, let's check and see if it conditionally converges. Okay, well, now let's check conditional convergence. All right. Now, to check conditional convergence, we're going to actually look at the series. N equals 1 to infinity of -1 to the n square root of n over n plus 1. Well, to check conditional convergence just means do the same thing, just do not use absolute value. Because when we use the absolute value, we get something different altogether. This here is not the same as this. This sequence is not the same as this sequence. This series is not the same as this series. So now that we're checking conditional convergence, right, we look at our series, and as we're looking at the series, we have to determine which test are we going to use to see if it converges or diverges. Since there's a -1 to the n, I'm going to use the alternate series test. All right? Let's use the alternate series test. Because it's -1 quantity to the power of n. It looks like this. Where is it? Right here. We're going to use the alternate series test. And the alternate series test has 3 conditions. An is positive, An is decreasing, and An, the limit of it, equals 0. Let's see. All right. So, An is positive. Well, not equal 1, it's positive. an is greater than 0. That just simply means whatever value you put in for n, well, hold on. Before I do that, let me write it out again. Let me tell you exactly what an is. An equals the square root of n over n plus 1. That's what an is. That's first. That's an. Here come the conditions. An is greater than 0. That means it's positive. Whatever value greater than 1, if you put a 1 in here for n, positive. Now take that and go up to infinity. Put a 2 in for n, positive. A 3 in for n, positive. So it's greater than 0. Alright? An is decreasing. An is decreasing. Now the way you show it's decreasing, you can take the derivative, and then once you have the derivative, evaluate it at any value from 1 to infinity, you will get negative outputs. That means that the sequence on the function itself is a decreasing function. Alright? We're going to forego that, but one way, a quick way you're going to look at it, plug in values, and you'll see it's decreasing, right? If you plug in 1, put 1 right here, you're going to get 1/2. That's what you get when n equals 1. Now plug in 2. You're going to get the square root of 2 over 3 when n equals 2. Now plug in 3. You're going to get the square root of 3 over 4. And these numbers, this is when n equals 3. And these numbers are getting smaller. They're getting smaller. Because the square root of 2 is like 0.9 or 0.9 something. It's a really small number. Okay? And so again, smaller denominator, larger fraction. Smaller denominator, larger than this one. So it's getting smaller as we go. Okay? So that's happening. It is decreasing. Last thing, check the limit. See if the limit, where is it? It's right, where is it? Where is it? It's right here, right here. Check the limit and make sure the limit as n gets large of an equals 0. Alright, let's see. Let's see. The limit as n gets to infinity of the square root of n over n plus 1, it does equal the limit as n gets increasingly large of n to the 1/2 divided by n plus 1, which does equal 0. Because the power in the numerator is smaller than the power in the denominator. So it equals 0. So therefore, by the alternate series test, the three conditions are true. So by the alternate series test, we can conclude that our sequence is going to absolutely converge. And it converges conditionally. And the condition is that you find the convergence without absolute value. All right. So therefore, the series n equals 1 to infinity of -1 to the n square root of n divided by n plus 1, it converges conditionally. There you go. We proved by way of the limit comparison test after we went through ratio, after we went through direct comparison, but we proved by the limit comparison test, hint, hint, the limit comparison test, that's a good test. That's a good test. Anyway, all of them are good, okay? But we proved by the limit comparison test that the series did not converge absolutely. Which means if it does not converge absolutely, if it diverges absolutely, it can still converge conditionally. A to the n can still converge conditionally. And it did converge conditionally by way of the alternate series test for convergence. You good? All right, take a break. Breathe a little bit. Just breathe, because we have many, many more examples to do. So take a break and breathe. All right? Okay. What's next? Here we go. Let's get some trigonometry involved. Okay, I think I want to, let me see how much more time. Okay, doing pretty good. The time is running, time is running. Time is running. Okay, next example. Example 4. Do some trading now. N equals 1, and we go into infinity, and we have -1 to the n of the cosine of n factorial over n to the n. -1 to the power of n times the cosine of n factorial divided by n to the n, that quantity. Does it absolutely converge? Does it conditionally converge? Or does it just diverge? First things first. N-term test for divergence. Let's see what we get. If we get 0, oh no! If we get 0. If we get anything else other than 0, that's called divergence. Come on, let's go. Alright, here we go. A subscript n is the cosine of n factorial divided by n to the power of n. That's an. Okay? Well, let's take a look at this limit here. The limit as n gets increasingly large of the cosine of n factorial over n to the power of n. Wow, that looks fascinating, doesn't it? Sir, what's the limit as n goes to infinity of the cosine of n factorial divided by n to the n? Really? Okay, step 1. First things first, ladies and gentlemen. Look, why don't we consider the limit as n goes to infinity of just the argument of just n factorial over n to the power of n, and go back to the comparative growth rates. That's all. Let's do that. Look at the comparative growth rates. Okay? This is factorial. My denominator is a variable exponent. And this red is getting kind of on his last leg. Okay, look at that. Which one is growing slower? Which one's growing slower, the factorial or the variable exponent? And if you say that the factorial is growing slower, then you are correct. So we have something that's going slow in the numerator over, function that's going fast in the denominator. So slow growth rate divided by fast growth rate as n gets increasingly large and going to infinity, that is 0. That's 0. So here's what it means. It means this whole thing right here this is going to 0 because the variable exponents, right? Well, yeah, I can say variable exponents, but let's call it what it is. The variable exponentials. The variable exponentials. They grow much faster than factorials. So that goes to 0. So now, since we know that this right here is going to 0, now let's look at the limit as n approaches infinity of the cosine. Now take this out and put in 0. Does anyone recall what the cosine of 0? Good. If you say the cosine of 0 is 0, then you are absolutely incorrect. Absolutely wrong. Cosine of 0 is 1. Which means the limit as n goes to infinity of the cosine of n factorial divided by n to the power of n, it equals 1. Which means, since it equals 1, and 1 does not equal 0, then this series is divergent. Therefore, series is divergent because of the nth term test for divergence. It is divergent. And that's it for that problem. You're done. Yay! Oh my goodness. All right. Let's go another one. Here we go. Example 5. Example 5. Okay, let me see what we have here next. All right, here we go. Let's turn it around. N equals 1 to infinity of n to the n. All over n factorial. Okay? So first, let's check for, let's check to see if we have some divergence here, or let's use the nth term test on this fella first. So what is a to the n? A to the n is n to the power of n all over n factorial. So the limit as n gets increasingly large of n to the n over n factorial, that's going to equal, what do we have here? Well, we're going to have something that's very, very large. N to the n is very, very large. So we have the variable exponential divided by the factorial. And this right here is infinity. That gets infinitely large because we have the larger divided by the smaller. And whenever you have the larger divided by the smaller, it's going to get infinitely large because you can be as large as you want to be. And no matter what, you have smaller dividing into that, the quotient of that is still going to be large. So this goes to infinity. All right? Infinity does not equal 0. So this fella is divergent. There you go. It's divergent. That's it. It's divergent. Because of the nth term test for divergence. Therefore, series is divergent because of nth term test for divergence. There you go. It's divergent. Look, if you don't believe it, watch this. Watch this. If you're like, yeah, Mr. Right, but I don't know about that one, man. That nth term test for divergence, getting the answer of infinity. Yeah, I don't know. That doesn't seem like it's divergent to me. Well, I tell you what. Well, then do this. Since I see factorials and powers of n, let's look at the ratio test. Let's put the ratio test on it. Let's see what the ratio test is going to do to it. Let's look at the ratio test. So let's look at n equals 1 to infinity, absolute value of n to the n over n factorial. Let's put the ratio test on it for absolute convergence. Let's see what it does. Okay? So, here we go. Limit as n goes to infinity of all of this plus 1. So it's going to be n plus 1 to the n plus 1 divided by n plus 1 factorial times. Take this, the reciprocal of it, flip it. N factorial divided by n to the n. Algebraically manipulate it, separate it out, rewrite it. So here we go. So if I do that, I'm going to have the limit as n goes to infinity, right? Now watch how I write n plus 1. That's going to be n plus 1 to the n times n plus 1. That's what that is. Times n factorial, all divided by, now n factorial, or n plus 1 quantity factorial, I'm going to write that, well, look, n plus 1 quantity factorial is n plus 1 times n factorial. So I'm going to write this like that. So I'm going to put the n plus 1 underneath n plus 1. I'm going to put the n factorial underneath n factorial. And then I have here n to the n times n to the n. I can cancel some things now. This goes. Okay. I'm left with, stay with me, the limit as n goes to infinity of, I'm going to write this as one expression now. I'm going to write it as n plus 1 over n all to the power of n. See how I rewrote this? I wrote it as n plus 1 over n quantity to the power of n. Now I'm going to go inside the parentheses and simplify it. And that's going to give me, here we go, the limit as n goes to infinity of 1 plus 1 over n to the n. And we all know what this is. You know what this is. You know what the limit as n gets increasingly large of the quantity 1 plus 1 over n to the power of n. That's just simply e. That's the number e. This equals e, which is approximately 2.718281828 ... That's the number e. And guess what, ladies and gentlemen? E is greater than 1. And so since E is greater than 1, if I use the ratio test, right, and if my limit is greater than 1, then the series does what? Diverges. You see that? So the nth term test told us it diverges. But if you want to take it a step further and do further proofs of it, well, there you go. The ratio test also tells you that it is what? It diverges. Okay. Let's see. Let's look at one more example. Let's do one more. Let's do one more and let's see if it's going to absolutely converge or diverge. Let's see, this is example 6, I believe. Check my time here. Yeah. Example 6. All right. Which one do we want here? Let's see. Let's look at the limit. No, not limit. We got stuff. Let's start with limit. We got to start with the series. The series. As n equals 1 to infinity of cosine squared n plus 1 divided by n squared plus 2. Yeah. Let's take a look at that one. And let's see what that's going to do. Okay, first, you might want to consider the nth term test for divergence. Okay, consider the nth term test for divergence. And let's take a look at the limit of this thing here. Okay, now when you have this cosine squared n, right? If you know anything about the graph of cosine and the graph of sine, you know that cosine and sine, it fluctuates between, -1 and 1. Cosine and sine. The range is from -1 up to +1, okay? Including -1 and +1. That's the range. In this case, it's cosine squared. Anytime you square a number, right, we're going to get a positive output. We're not going to get necessarily a negative output. It's going to be positive. And in having a positive output, that also means that cosine squared is going to go in between 0 and 1. That's how cosine squared fluctuates. Whereas cosine itself is between -1 and 1. But not squared. Because once you square whatever that angle is, you're not going to get a negative output. The output is going to be 0 or greater than 0 up to 1. It's not going to be negative. Okay? And so, if we look at this cosine squared, here's how you want to approach this problem. This cosine squared has what we call an upper bound. Of 1. It has an upper bound of 1. So since it has an upper bound of 1, then we have to consider the cosine squared of n plus 1 divided by n squared plus 2 has to be less than or equal to. The upper bound here is 1, and 1 here, 1 plus 1 is 2. So this has to be less than or equal to 2 divided by n squared plus 2. All right? So, here we go. The sum n up to infinity, cosine squared n plus 1 divided by n squared plus 2, absolute value of that has to be less than or equal to the sum of n equals 1 up to infinity of 2 over n squared plus 2, absolute value here. Okay? So this has to be less than that, because the most our numerator can be is 2. That's the most. Okay? That's the most it could be is 2. If the cosine or whatever the angle n is give us an output of 1. Alright? So whatever the cosine of the angle n is, and you square it, the most it could do is give us an output of 1. So 1 plus 1 is 2. So this quantity is going to be greater than or equal to this one. Alright? And then I can take this and I can compare this one to the absolute value of, okay, I noticed this right here. 2 has to be 2 over n squared. So this an has to be less than bn, which has to be less than cn. Okay? And I know exactly what this one's going to do. I know what that's doing. What is that called? What test would you use on that series? What test would you use on this series? This series, you can rewrite it like the 2. You can take this 2 and just bring it out front. So it's 2 times the summation. N equals 1 to infinity of absolute value of 1 over n squared. That's 1 over n squared. And what does this series do? That series converges because it's a p-series. So, therefore, the series absolutely converges. Because of p-series. It absolutely converges because of the p-series. And there you go. So, I jumped into this problem. I really didn't even look at the interim test for divergence. I'm sorry. Look, the interim test for divergence, it simply says the limit as n goes to infinity of the cosine squared of n plus 1 all over n squared plus 2. This right here, that goes into infinity. This right here at most goes to 2. And 2 divided by a very large number, right, is 0. Which means the n-term test for divergence is inconclusive. Maybe that's why I just went past it. Because it's inconclusive. It tells us nothing. It tells us that our limit is 0. Okay? Because we have 2 over a very large number, which goes to 0. So there you have it. Okay. That was kind of long, I know. But that's absolute convergence. And conditional convergence and divergence. So, thank you for giving me some of your attention. I hope this really helped you. If you have any questions, comments, please comment down below, or you can send me an email. All right? Stay safe. Stay home. Keep your hands washed. Keep your hands clean. And whatever you do, because life is good, whatever you do, stay positive. Okay? All right. I'll see you next time.